This is Lecture 14 in the series of lectures on fiber optics from the Fiber Optic Association. This lecture will discuss optical power measurements. Optical power is the basis of most measurements for fiber optic testing. We use it to measure the output of optical fibers so we can determine the output of transmitters or the inputs of receivers. We use it as references for measurements of optical loss. We use it for calibrating the trace on an optical time domain reflectometer. In order to allow different people making measurements in different areas in different countries to all be comparable, optical power is calibrated to international standards. To measure optical power, we use an instrument called fiber optic power meter. It's basically a specialized light meter with adaptation for fiber optic connectors. It's designed to capture all the light coming out of the fiber, measure it, and calibrate the power at the typical wavelengths we use in fiber optics, 850, 1300, and 1550 nanometers. Most power meters measure in both dBm and dB, and we'll explain what that means shortly. Power meter has a digital display that shows the output power from the fiber, the range of the measurement, and the wavelength. The wavelength calibration is done at 850, 1300, and 1550 nanometers. Those are the wavelengths that international standards groups have agreed upon for calibration. The range is in dB or dBm and sometimes in linear scales in watts. Some meters have a push to zero to allow us to set a 0 dB reference also. That's not calibrated, it's different for every measurement. Typically, fiber optic power meters are adaptable to a variety of different fiber optic connectors. Perhaps not as many as shown here, but at least a typical power meter will adapt to ST, SC, and LC fiber optic connectors. The standard way of measuring optical power is covered in a TIA standard FOTP 95, and it's accepted internationally. Basically, we connect a calibrated optical power meter to the cable. We set it to the correct wavelength, and we measure the input in dBm or watts. dB is a logarithmic scale. It's called dB or decibels, and it's 10 times the log of the ratio of two powers. So a ratio of a factor of 10 becomes 10 dB, a ratio of 0 becomes 1 dB on a log scale, 3 dB is a factor of 2, and a minus 10 dB would be a factor of 1/10. dBm is very similar, except the dB is referenced to 1 milliwatt. So 0 dBm becomes 1 milliwatt, minus 10 dBm would be 1/10 of a milliwatt, and 10 dBm would be 10 milliwatts. Here's the relationship of dBm and optical power in watts shown graphically. This graph covers a range of 10 to the 7th, 10 million to 1, or 70 dB, and it covers pretty much the range of which we make measurements from fiber optics. Lasers, for example, have about a 0 dBm output. Optical amplifiers can have plus 20 dB of output, and LEDs may be down in the minus 10 range. Receiver power typically can go down to minus 30 or even further. Fiber optic power meters typically use solid-state detectors that are wavelength sensitive. For short wavelengths, we use silicon detectors, and for long wavelengths, we use germanium or indium gallium arsenide. Because the sensitivity of the detectors depends on wavelength, we have to calibrate them carefully at the typical wavelengths we use in fiber optics, at 850, 1300, and 1550 nanometers. And when you're measuring optical power, it's important to set the wavelength calibration of the fiber optic power meter to the wavelength of the source you're testing. Fiber optic power meters are calibrated to national standards, like NIST in the US, using transfer standards sent to manufacturers for calibration. NIST basically provides standards that are calibrated at 850, 1300, and 1550 nanometers, and manufacturers adjust their calibrations to agree with the NIST standards. However, the process of transferring the standards to manufacturers means that typically there's about a 5% uncertainty compared to NIST standards. Just to make sure that power is read correctly, meters should be recalibrated every year or whenever repaired. The uncertainty of an optical power meter measurement depends on the calibration, the source wavelength and spectral width, the coupling to the meter, and dirt, because it's very important to clean the connectors before you couple it to the meter to measure the optical power, and it's important to occasionally clean the detector in the power meter itself. Be sure to view the other testing lectures on the FOA YouTube channel and read the pages on the FOA Online Reference Guide website. We're the FOA, the Worldwide Professional Society of Fiber Optics. Be sure to go to our website for all the technical information you can find there.